All right, hello friends, welcome to a new week. So we finished up talking about graphs, and now it's time for trees, which you already know from CSCI 41. So what we're going to do is cover them again from the perspective of kind of graphs, okay? Because trees are really very specialized versions of graphs, okay? So let us get started, and the trees that we'll look at are not just the kind that we talked about in CSCI 41 that have a root. There's a kind of tree that doesn't have a root. Okay, so we'll talk about that too. So yeah, a tree, it's just an undirected graph. See where this is all going? It's an undirected graph that's connected, so everybody can talk to each other. There is a path, okay? And it has no cycles, okay? So those are very important things. That's what it means to be a tree. Those are the definitions that make something, that make a particular kind of graph a tree. Okay, it's got to be connected, and it's got to have no cycles at all. Okay, so that's exactly why your book put trees after graphs, and that was a good idea, I think. So yeah, we know and love from CSCI 41 trees that have roots, and so there's like a first node, maybe a pointer to that first node that you can get to, and then you can go left or right, or in the middle, perhaps. Yeah. Some trees have root nodes, others do not. They just exist. Like, maybe that's a root. That could be a root if you wanted it to be. But it doesn't have to. Like, any of these could potentially be a root. You could just, like, hold it with your finger and let the rest, like, flop down, right? It would be a tree no matter what. So that's the idea. So, yeah, these are free trees, and these are rooted trees. Okay? So, the trees with roots are just called rooted trees. And you can have as many children as you want. You don't just have to have two, because in CSCI 41 we talked about binary trees a lot, right? You can drop the binary requirement as well. Okay, so here are some nice memes if you would like to pause about trees. So the way that we draw them makes us think that we're like doing things upside down, so like trees in real life versus... Yeah. This is what a tree looks like in computer science, right? That's the beauty of the meme. So yeah, let's talk about some terms because we're learning new stuff. We gotta learn all the fancy terms as well. So, just like graphs, of course, it is a graph. A tree is a graph. There are vertices in play. There are edges between vertices, right? So we have concepts like level. The level of a vertex is its distance from the root. So this is all about rooted trees right now, because those are trees that we like to use a whole lot. So the distance from the root, so B here is the root in this tree, and the level of a vertex is its distance from the root. So B lives at level 0. A, E, and D, they all live at level 1. Yeah? And like C, for example, is at level 1, 2, 3. Yeah, because it's 3 away from the root. 3 edges you got to follow. All right, and because there's a root, there's a notion of hierarchy. So there are parents and children, right? That's the metaphor. So like C has a parent, its immediate parent is H. Like its grandparent is D. See that? Isn't that nice? And so similarly, or vice versa, H is the parent of C, and C is H's child. Okay, that's the idea. So A is B's child, E is B's child, F is E's child. And if you do it the other way, B is A's parent. Yeah, that's the idea. Not too bad. And then if you go up, you got your parents, your grandparents, your great-grandparents. We just call those ancestors. So every vertex on a path. So like if we were talking about G right now, all of its ancestors are H and D and B. See that? That's the idea. And then leaves, we love leaves. Those are at the edge of a tree. Those are all the nodes that have no children. Okay, so all of these that I'm circling are leaves because they don't have any children. There's like nothing there. In C++, we use null pointers for that. Yeah, so those are all leaves. And then it's quite nice, recursively, tree structure is a recursive thing because you can talk about subtrees. You can like say, all right, I'm going to pick a new root given this tree, and then I'm going to consider everything below it and pretend that that thing was really the root. So for example, here is a subtree. Let me draw it in green. I can just like be like, okay, I'll circle this. let's consider the subtree rooted at D. And you see how this is a complete tree all over again? That's the beauty of it. Okay, so this is just another, this is a subtree. Okay, it's again a tree because of the tree properties. You just pick a new root and you suddenly have another tree. Like, for example, here's another subtree. Here's another subtree instead of that. Here's another subtree with just one node. See that? Not too bad. And the beauty of trees, one thing that makes it nice for algorithms that use trees, is that there is a unique path from every node to every other node. Because it's connected, there are no cycles. Those imply, those definitions of a tree imply that there's only one way to get from B to G. You have to go right, you have to go left, you have to go right. That's the only way you can possibly get to G. And we're going to prove that later in the class. Okay, so that is all the terms. Some of these should be familiar, but now we're looking at things from a different lens, right? From the graph perspective. Okay, so now I want you to do some stuff, but I'm going to draw a tree with at least 4 levels, sure. So 1, 2, 3, sorry, 1, 2, 3, 4. Now we got 4 levels, and let me like make it prettier. Let's do some stuff like that. I'll draw a binary tree because we like to use binary trees a lot. So here's my tree, and I'm going to label, sure, past Lawton, I will label these with n, no, let's do n here. Let's do I don't know, here, and let's do, I don't know, D, and what am I asking about H? Let's do, gosh, this is a hard one. Let's do D here and then H here. Yeah. So that is my tree. Please take a second to do all of these. It shouldn't be too long, but based on this tree. Okay, this is my tree for you. Okay, and then we'll come back and we'll do it together. So the first question is, which vertices are ancestors of vertex n? Okay, so if we go back to the definition, every vertex from a node to the root, excluding that first node, is an ancestor. Okay, so it's, you aren't your own ancestor, which is maybe nice to know. So this is not the ancestor, but H is, and let me like label the rest of these with a different color, like, I don't know, A, B, C, use D, so E and F. Those are my node names. All right, so ancestors of n are going to be H and A. See that? You just go up to the root. This is the root. A is the root. Okay, so this is H and A. Those are the vertices that are ancestors. And then, okay, let's talk about the descendants of vertex I. So we go to I, and we look at its descendants. So it's the inverse relationship. If U is V's ancestor, then V is U's descendant. So it's just everybody that has I as an ancestor, which is E and F. See that? So we got E and F. I'll be lazy and not draw the braces. Okay, tell me all the leaves in this tree. Okay, those are the ones without any children. And I think you can see them pretty quickly. You got C, B, D, F, and E. Yeah, those are the leaves. C, E, F, D, and B. Okay. All right, what's the level of vertex D? And that's, again, the distance of that node from the root. So you got level 0, 1, 2, 3. D is at level 3. Okay, and so is I. What's the height of the tree? Let's see here. That is something that I didn't write here, but maybe I should. The height of the tree is just the max level. That's all. Okay, so the max level is the height of the tree. So for example, this height has this tree has 4 levels total, so the height of the tree would be 4. Okay, it's the max level. And let me move this down over to here. There we go. And so yeah, that is the height. And boop. Now let's figure out which vertices are at level 3. And I think I already did that. That's quite nice. We have I and D. Okay. Draw the subtree rooted at vertex H. There's vertex H. The subtree, rooted at vertex h, I'm just going to circle it. It's this. You pretend that h is the root, and then like this is level 0, level 1, level 2, level 3 now. See that? That's the idea. Okay, so I did that in green. And then what are the siblings of vertex I? Can you guess what this is? What sibling means? So I didn't write it here again, I don't think, but sibling, all that means is who's at your level, like who are you next to, right? So like the sibling of I, related by a parent, right, is going to be D. Okay, so just D is a sibling of I right now, and that solves it all. So hopefully that wasn't too bad. Lots of terms and getting practice with them. And now let's move on to a nice theorem that's good to know. So there is a unique path between every pair of vertices in a tree. Okay, so if you want to get from somewhere to somewhere else, there's only one way for you to go. Okay, there's a unique path. So for example, if I want to go from here to here, I am forced to go left and right. See, there's a unique path no matter which, actually, even in a free tree, no matter which two nodes you circle, there's only one way to get there. See that? Without repeating yourself. That's what it means to be a path, right? So let's prove that. There's a unique path between every pair of vertices in a tree, and we're going to do this by contradiction. So pretend there is to assume, for a contradiction, that there are two paths that are not the same. Let's call them P and Q, between a certain pair of vertices. That's how we do the negation of that theorem, right? Between vertices U and V. Okay, so assume that there are two paths, P and Q, between vertices U and V. Let me draw that. So here's my U, here's my V, and here is path 1. Here's path P. That's path P. And here is path Q. Take some other weird route. That's Q, that's P. What I'm going to prove to you is that there's a cycle here somewhere. Okay? There is secretly a cycle between P and Q because they eventually, they come together. If there aren't any vertices shared along P and Q, you can just go in a circle like that, you got a path. But I'm going to show you a cycle, no matter what. So the idea is P and Q have a very certain shape. So here's P, here's Q. They are going to disagree on at least one vertex, okay? At least one vertex. They're going to branch off, and they're going to come back together eventually, though. Okay, so these paths have to look like this. So this is like the last vertices where they were the same. P and Q were following the same places for a second, and then they come back eventually, but they do differ. They're not the same path. So they're going off in two different directions somewhere, and they're coming back together eventually. Okay, that's the idea. And my hand-wavy proof to you is that where they go off and come back together is a cycle. Okay? If we assume that this exists, we have just found a cycle between these two nodes. You can go this way and back around. A cycle. And, well, because we know we have a tree, and we assumed all this, the definition of a tree is that we have no cycles. And we just found one, which means that we have found a contradiction. So that's a contradiction. If we have two different paths to the same place, there is some way to get a cycle, okay? Eventually they're going to disagree and split off, and they have to come back together because they're both going to V, okay? That is the proof. They have to come back together. So where they split off and where they come back together, those make a cycle, okay? That's the idea. Contradiction, and that proves our theorem. So there's a unique path between every pair of vertices in a tree, which is nice because there's only ever one way to get somewhere. Okay, and the next proof that I want to give you is a lemma. It's getting ready for this theorem. Okay, this is in preparation for the theorem on the next slide. I should say. So here we go. Put that up here. And so this theorem that we eventually want to prove is that if a tree has n vertices and m edges, then m equals n minus 1. That's a very exact thing to want. So if you have n vertices in a tree, that tells you exactly how many edges you are, that you have. Okay, and in order to prove that, we need this lemma that says any tree with at least 2 vertices has at least 2 leaves. We'll need that. Okay, so let's prove this eventually by contradiction. I want you to find the longest path in the tree. Okay, so here's our tree. It's all fancy and it's got nodes all over the place. There is a path that is the longest path. There might be multiple that have the same length, but there's one at least that is quite long. Okay, so that's, let's say that it goes from U to V again. Okay, the first and last vertices on this longest path through this tree look like this, starting at U going to V. Okay, we're going to show by contradiction, we're going to prove that U and V must both be leaves. Okay, and this is all going to work because the tree has at least 2 vertices. Like here's the smallest tree with at least 2 vertices. Obviously there are 2 leaves, right? So doesn't matter how many more there are, we have U and V, that's the longest path. Okay, the fact that it's the longest path is going to give us this contradiction. Okay, so the step goes, okay, assume that U and V aren't. Assume that they are not leaves. I'm going to give you a contradiction. Let me show you. What would happen if they aren't leaves? They have edges going out of them, right? They are going to other vertices. This is the longest path, remember, in the tree, right here. It's called P. It's the longest path going from U to V. And we're saying that U and V aren't leaves. Oh man, that means that U and V, they go off in other directions to other places. And what do you know? If we were to go along those directions, like maybe U has children of its children, if we were to go off, we would have a longer path in the tree, wouldn't we? Because we aren't touching these places. Boop, boop, that's a longer path. That's a longer path. That's a new longer path. And that's a contradiction. But then we'd have a longer path. A longest path. Contradiction. Which means that U and V are both leaves, and so we have at least 2 vertices. Sorry, there are at least 2 leaves in this tree. QED. Please yell at me if this is not making sense. Contradiction is really good to prove things like this. Okay, we've used it twice now. So now we can use this lemma. Every tree we know, if it has at least 2 vertices, it has at least 2 leaves. We can now prove, dun dun dun, that if you have a tree with n vertices and m edges, then you are forced to have m equal n minus 1. And let me just show you that, just quickly, intuitively, why it has to happen. Here is my tree. It's got 1, 2, 3, 4, 5, 6 vertices. How many edges? Well, 1, 2, 3, 4, 5. It's always one less. Okay, so that's my example. It's not a proof, just an example. Let me prove to you, beyond a shadow of a doubt, that every tree, no matter what it looks like, make it as weird looking as you want, it has n minus 1 edges. Okay, so we're going to do a proof by induction on n, because this lets us have a theorem that's true for all n, no matter what it is. Okay, so let's pretend that we have the smallest possible tree. So let's do our base case. N equals 1, we have to show that m equals n minus 1, which equals 1 minus 1, which equals 0. So if we have just one node in our tree, it look like this. It has no edges. Yeah, it's its own little leaf, and that is proving the base case. Yes? So yes, of course, any tree with one node has no edges. Makes sense. And now we do our inductive step. We get to assume that this is true for a smaller number and then prove it for the next bigger number. So our inductive hypothesis is, well, we'll get there in a second. We have to prove that a tree with k plus 1 vertices has m equals n minus 1, which is just k edges, right? That's all we need to show for our inductive step. We assume that n equals k plus 1. And we show that this works for a tree with k plus 1 vertices, but we get to assume our inductive hypothesis is if we can somehow break down the tree, we get to assume that a tree with k vertices, that's one smaller, we get to assume this, it totally has k minus 1 edges. And we can use this inductive hypothesis to prove our inductive step for the one bigger, the k plus 1 sized tree. Okay, so here's the idea. Dun dun dun, we have a tree. It has more than one node. So n is greater than or equal to 2. Oh man, is that useful to know. And so it looks something weird like this. This is our tree. It's like a cloud. Maybe I should draw a cloud. It's got some nodes, it's got some edges. It's moving around. That's our tree. And what we can do to this tree, though, is we can find a leaf, okay? So find a leaf. We know we at least have one by the lemma. And consider the tree without that node. So find a leaf in this tree. We know we can find one by the lemma, okay? The lemma gives us the fact that we can find at least one leaf in this tree. We know it has size greater than or equal to 2. So find a leaf, maybe like here's one, and consider the tree without that node and that edge that's connecting it, okay? That node slash edge to that leaf. This is a subtree, yes, isn't it? That subtree is of size what? That subtree has one less node, which is, oh, k nodes. K vertices. Which means we get to use the inductive hypothesis. We can assume, because it's a smaller k, therefore the subtree, let me draw that a bit better. Therefore the subtree has k minus 1 edges. We just need to prove this for the bigger tree, which has what? One more node, one more edge. Oh shoot. Okay, therefore, original tree, we just plop on that one last edge, has how many edges? K edges. It's k minus 1 plus 1. And that proves our inductive step. You see that? Isn't that beautiful? That is a lovely, lovely proof, in my opinion. So we just found a smaller tree, which means we can use the inductive hypothesis because we can assume that our theorem is true for a smaller tree. And we just like surgically removed and then added right back this leaf. And that made the tree slightly larger again, but we knew something about that subtree. And we could add on one extra node. We knew we could add on one extra edge and get the number that we were looking for. Okay, so that is a very fun little proof, and that is very, very good practice for the following thing that I would like you to try. Okay, so let me give you a whole lot more room, or at least me a whole lot more room to draw on the answer, is what I want you to do is prove in a very similar way that if you have a forest, and a forest was a lovely metaphor, it's just a bunch of trees. So a forest is a graph that has no cycles and that is not necessarily connected. So here's the idea. It's just a bunch of little trees interspersed. It doesn't have to be fully connected, but it's got a bunch of trees. That's why they call it a forest. It's beautiful. Okay, so prove that you have a forest. It has C components, like this one has three different components. And n vertices, it must have n minus c edges, which really essentially makes sense because of this theorem. But we have to use induction again to prove it. Okay, so you're going to do induction on n, and the base case will be n equals c, because we want to assume that n is greater than or equal to c. Otherwise, like, okay, we have 3 nodes and 2 components, that doesn't, or sorry, we have 4 components and 3 edges, that doesn't make any sense. You can only have n being greater than or equal to c. Okay, so this will be your base case, and that is that. So give this a try, and then we'll do it together. It'll be a very similar proof to this one over here. Let's make sure I'm still recording. Yes. Okay, so here is my proof. So by induction on n, we have a base case. We assume that n equals c. Okay, so we have a forest, and it has c components. It has just as many components as nodes in the tree, which means that, okay, if it has like 3 components and 3 nodes, the only arrangement of these nodes are, they're all separate. You see that? They have to all be separate. There are no edges at all. Okay, so if n equals c, we have to prove that, to show the edges equals, let's see, n minus c, which equals n minus n, which equals 0. And I think I just showed you that. If you have just as many components as you do vertices, you cannot have any edges. So if n equals 5, c equals 5, yeah, there's nobody touching, because the second you add an edge, now c equals 4. There are 4 components only. This one, this one, this one, and this one. So if you have the same number of components as nodes, you must necessarily have no edges. Okay? And so by a drawing, that made sense. So that proves the base case. Let's do the inductive step now. Okay, so now we have n is greater than c. We know that for sure. Let's just pretend that n equals, I don't know, k plus 1. Yeah. And so what we need to show is that the forest has how many edges? The number of edges equals n minus c, which is equal to k plus 1 minus c, right? Because k plus 1 is n. Okay, so we need to show that, and we can use the inductive hypothesis, which gives us that if we have a one smaller forest, if n equals k, then the number of edges, and c was the same, equals k minus c, because n would equal k at that point. We get to assume that the theorem holds for that smaller value. Okay, so we get to use this inductive hypothesis if we can make a smaller forest out of the one we've got. We have a forest of size k plus 1 right now. And the idea is we have a forest with more nodes than components. See that? We have more nodes than components, which means we must have at least one component with 2 nodes. You see that? There has to be one of these connected somewhere, okay? 2 nodes must touch each other, otherwise you would have n equals c. So there exists a component of size greater than 1. Pick that one and play the same game, because now we can again find a leaf. Pick out a leaf and consider that subforest. So it's like, here's our forest. Find a leaf, we're guaranteed to have one. So here's one. and chop this off and consider the whole rest of the thing. That's our subforest with a smaller value of numbers of nodes. Oh man. And the inductive hypothesis gives us the fact that the edges are k minus c. Okay. So that subforest, it has k minus c edges. When we add back that leaf node with that one edge, adding back the leaf into that forest, into that component of the forest, adds one more edge. So, therefore, the number of edges in the whole thing, in the original tree, equals, well, whatever it was for the subforest, which was k minus c, plus 1, which is the same as what we wanted to show, k plus 1 minus c. Bam! Wasn't that fun? So that's very, very similar to this one, but there's a bit of a trick in the fact that we had to know like what our base case should be and what our inductive step should be, because we needed to use the fact that we had more nodes than components to be able to figure out that, oh, one of those components has edges, which means, oh man, it has at least 2 leaves. Let's take one of those. Let's do surgery, mathematical surgery. Okay, so that is another fun little proof, and hopefully this is making induction a bit more strongly ingrained in your mind. Yeah. So that is that. Forests are fun. Another question for you. So let's pretend that we have this. Okay, so we want to pretend that we have an undirected graph, call it G, with n vertices and m edges. We don't know how many, but we got a graph. We want to prove that if m is less than n minus 1, then G must not be connected. Okay, so we need to show that, okay, no matter what the graph is, it could be a tree, it doesn't have to be a tree. If m is less than n minus 1, then G cannot be connected. Let's see what we have here. This is definitely greater than, so I think it's forced to be a tree. So here we go. And take a second to think about this. This is obviously a very difficult question, but I want you to think about how you might prove it, okay? And think about how can you use the fact that trees have exactly n minus 1 edges in your proof, okay? So give that a shot, and then I'm going to show you the secret. So the secret is to show that G is a tree, or at least it should be a tree. It's not even a tree because it's got even less edges, but we're going to get to there and then use this fact, okay? So we're going to do this by contradiction, I guess, again. So proof by contradiction. I think, yeah, let's assume the number of edges is less than n minus 1, number of nodes minus 1, and assume that G is connected. We're going to show that there's a contradiction. And there's a little subproof involved. So I want to also show that G has no cycles. G cannot have a cycles with this edge count. Okay? Let me prove that to you. Just hand wavily. So here is my graph. It is connected, because we're assuming it is, of course. So it's at least a tree, right? It's at least a tree, but maybe it has a cycle, okay? And the idea is, if it's a tree, it's connected. If it's connected, and it has n minus 1 edges, right? Exactly. And if you have a cycle, you have even more edges than that, okay? You have a cycle that's connecting 2 unnecessary edges, 2 unnecessary vertices, sorry, that don't need to be connected. They don't need that edge to be connected still. Okay, so you have more nodes than you would in a tree. There's more edges than you would in a tree. I keep getting those terms confused, sorry. So you have more edges than you would in a tree, which is greater than n minus 1. greater than n minus 1. So G can't have any cycles, okay? And that's where the magic happens. G can't have cycles. Because of that edge count. It's smaller than a tree would have. And now the beauty is, that means G should be a tree. G is connected, it has no cycles, so G is a tree. But we have proved that every tree with n vertices better have n minus 1 edges. So if G is a tree, so G has n minus 1 edges. That is, m equals n minus 1. And we just assumed that m is smaller than n minus 1. Okay? So the fact that we proved that G must be a tree, because it can't have cycles, and the fact that we know that trees have a certain number of edges contradicts with our assumption. Okay? And that is our proof. Okay, so you cannot have less than n minus 1 edges and still be connected. Okay? That's the idea. It says nothing about having more than that edges and still not being connected, because you can have a ton of edges over here, and now m is greater than n, but you're still not connected. But if you have, it's saying if you have too few, there is a number that is too few, and it's guaranteed to not be connected in that case. Okay? So that is the idea there. Hopefully that wasn't too bad. Now, moving on to ways to get around trees. Okay, so this is a very, very important thing that I want to talk about. It's called tree traversals. Okay, so the first two that I want to introduce to you are called pre-order and post-order. Pre-order and post-order. These are the algorithms. They're just ways of visiting every node, processing every node, just like we did for graphs. Okay, we often want to process all those nodes in a tree, and we want to decide the order a whole lot of the time. We want to make sure to visit the root first, or the root last, and in a certain recursive order. And so these are a bunch of recursive algorithms that I'm about to throw at you. Okay, so pre-order, if you want to visit all the nodes of a tree, you can potentially visit the higher up nodes first. So visit the root first, and then recursively visit the children. That's what pre-order gives to you. Okay, recursively visits those children. That's what pre-order does. And here's what it looks like in code. It's, okay, pre-order, starting at some node, some vertex in the tree. Well, first, process that node. So it'll hit the root first if you give it the root to process. And then, for every child, run pre-order on those to recursively process the rest of them. Okay? So that is all pre-order is. And you can pretend like process means print. I'll show you what that means soon. And post-order is the opposite. It's you want to recursively visit the children first and then visit the root. So this ends up visiting the root node very last, right? Because like here's your tree. You always give the root first. And so you'll say like pre-order. Pre-order V, post-order V, where V is the root. Okay? That's what you give first. And so maybe I should use R instead of V just to drive the point home. It's just a parameter. Just an argument. R. Okay? So these are two equally valid ways to go through an entire tree and visit all the nodes. Okay? Post-order, you might be looking at this and notice that it's really depth-first search for trees, because what it's doing is it's going as deep as possible first, like going to the children and to their children and to their children. And then at the very end of all of that, it's like working its way back up. And okay, let's process the node. Let's process all these other nodes. It's just building up a stack of computation because of these recursive calls. Okay, so let me give you some examples to make this make this have a whole lot more sense. And this is the root. Okay, we always start from the root when we're traversing. And let me show you the pre-order and the post-order traversals of this tree. So remember the algorithms. Okay, For pre-order, we first process our current node and then we recursively process every child. Okay? So let's first do pre-order. And pre-order is always root, visit root, then visit all the children, recursively visit children. And you do it from left to right. Okay, so if we're calling like pre-order on D, the root, that's the first thing we do, that's our stack. We're going to run this code, visit the root, which essentially prints out that D, and then we're going to recursively visit the children, and so that means we're going to do this. We're going to be like, okay, let's go to G, pre-order on G, and let's do this whole thing on G now. So visit its root, it's the subtree now. So it's like we're giving this root now to the pre-order function. And so we visit G first. Okay, so we visit, it's now the root, and then we recursively visit G's children. And so we're going to do pre-order from left to right on C. Okay, and so we're going to visit C, pretend that it's a subtree, and it's the root of that subtree. We'll visit it, and then all of its children, but it has no children. Okay, so we'll visit C, recursively visit its children, visit E, after we're done with C, of course. So yeah. And then finally, after we visited C, we're going to pop it off because we're done with pre-order for C itself. It has no children, it's done. It gets popped off the stack. Now we're back still trying to work on pre-ordering G. And we were here, we're recursively visiting the rest of the children. The other one is E. And so we'll do the pre-order on E, which is going to visit the root of this subtree, then recursively visit the children. There are none, so it's done. And now G is done because we recursively visited all of its children. And now we're back at D. We have to recursively visit the rest of its children. We did G, now it's time for B. So we're going to do pre of B. And so that's going to visit B, of course, and then recursively visit its children, but there are none. And so we're done. And so these will both get popped off the stack, and we are finished. So that's the pre-order order of visiting all the nodes. First it was D, then we recurse left. Visit the root first, though. G, then left, right. C, E. Okay? And then we're back up here and do B. That's the pre-order order. Okay? So think of like the pre and post as in, when do you visit the root? Okay? Pre means root first, post means root last. So post means children. And then root. Okay, post order, I guess. So let's now do the post order traversal of this tree and figure out how it's going to do that. So we're going to do post order again with the root. Post with D, and it's going to first try to recursively do the post order on the left and right. So the first recursive call goes to the left. So do the post order traversal on G, and then we'll, like, after we finish all the children, we'll eventually visit D, but that is only after we visited the children. So post is like, okay, G is my new subtree. Let me do my stuff. I'm going to visit all the children of G now. So let's go left and right. Let's recursively visit C, post order C. Okay, and so then we're going to recursively visit all the children of C. There are none. And then finally we can visit the root, which is C. So the very first thing we print out is, in fact, C this time. You see that? We went as deep as we could. It's depth first. So, and then we pop that off our call stack, and we're back trying to visit all of the children of G. We're not done. We got to visit E now. Post of E, and then we can do that one. We can visit all of its children. There are none. And then we visit the root of the subtree rooted at E, so we print our E. And now we are done visiting all the children of G, which means now it's finally time for the root. Yeah, so then we go to and visit G itself, and now we're finally done post-ordering G. Okay, so now we're back in D. We got to visit all of its children before we visit it. So let's go right now. Let's go and visit the B. Okay, so we're going to say post of B, and Okay, visit all of its children, there are none. Then visit it, the root of that subtree, rooted like this. So we visit the B, and then we're done. And finish with that. And now finally we visit all the children of D, so we can visit D itself. It was the root. Okay? So this is the difference in the orders. So we got your pre-order and we got your post-order. Okay? So that is the idea. And I think I do want to code this up in Racket for you. I'm not sure if I want to do it now or after the next slide. Let me do it after the next slide, maybe. Okay, so there are two other very common kinds of ways to traverse a tree. The first is called Inorder, which is kind of the third option when you have a binary tree. It only works for binary trees. You go first to the left, visit all the children recursively to the left, then you process your current node, and then you process all the children to the right. And so if you have a binary search tree like 42, 27, 88, I don't know, 33, and the Inorder, if you follow it, it will print out this in order: 27, 33, 42, 88. Okay, I encourage you to get accustomed to like how to calculate these things. And then breadth first search is exactly the same for graphs. You use a queue while it's not empty. You process the first thing at the front of the queue. I guess I should say front instead of pop, right? But technically you're popping from the front, whatever. And then you push all the children. So this works for, of course, non-binary trees. And so yeah, this is exactly the same as for breadth first search in graphs. It just looks a bit different, okay? And so then let me give you an example of how to do Inorder and breadth first for this tree. And then I'm going to show it to you in Racket, and then maybe we'll have one last crushed ice. So let's do Inorder, and then we'll do BFS. All right, so Inorder is going to start at the root, of course, and it's going to recursively go, it's always left, then root, then right, okay? So what's going to happen is, okay, first go left. We're working on these guys. Left, left, root, right. Okay, left, root, right. Let's go left. Left, root, right. Left. Okay, root, 1, right. There's nothing there again. Okay, now we're back here. Left, root, right. We're now at the root part. Okay, 1, 2. Then we go right. Okay, now it's left, nothing. Root, 5, right, nothing. Now we're back. We're done with all of these. Okay, then we are back to 7. We did all of the left. Now we do the root, the 7. Now we do all of the right, which again goes left. No, there's nothing there. Root, which is 9, and then right, which is 14. Okay, hopefully you caught that. That is the entire traversal of that, using Inorder traversal. It's always left, root, right, recursively. And then breadth first search is easy because it's level order. So I think you can tell very easily how it's going to work. I don't have to do it again. It's going to do 7, 2, 9, 1, 5, 14. It's going to go in that order like a little zipper. Just like that. Okay, so that's Inorder and BFS, and now I want to show them to you in Racket. I did pre-order, post-order, and in-order. Okay, so let me show you how I'm doing that there. Okay, so the first one was me making the trees. So I made a structure for trees, and every tree has 3 things inside of it: a data, a left, and a right. And I'm going to say that empty trees are null, and null in Racket is just the empty list. Okay, so that's quite nice. We can just use that because really we're going to be using null in C++ when we program this for real. So that's quite nice. So T1 is the first tree from that first slide up here. This is T1. Okay, I made C a leaf node, E a leaf node. It has no children, null and null, left and right. And then G is the parent of C and E, so it has a G and then a C and an E, like that. Okay, hopefully that's not too bad. That's what's going on there. And yeah, then we build up the B leaf node and then build up the root, which has G and B as children. which is all looking like that. G and B as children, which are their own subtrees. And then we give back D, because that's the whole tree. And then I did the same for T2. Okay, so it's a tree that looks like this. And so we can do pre-order, post-order, and in-order of all of those. And what we do, it's just a combination of, okay, when we actually have something here, when we have a real tree with a left and right in data, we will, for pre-order, first we worry about printing the data, then we visit the left child, then we visit the right child, all the left children and right children recursively. Okay, that's how you do it for pre-order, and then post-order and in-order are very similar. So post-order is first do left, right, then visit yourself. Then in-order is first do left, then yourself, then right. Okay, and this makes everything different. So if I go and run this, excuse me, if I go and run this on T1, which is this one, I can do post-order and pre-order just to confirm that this is all the same. Pre-order T1, and then post-order T1. We get everything that we saw before. Okay, so it's really going in that order. And then if we do in order of T2, we should get back the sorted version, okay, because it was a binary search tree. Okay, 1, 2, 5, 7, 9, 14. And it's just the magic of rearranging when you make the recursive call. It's very odd how that works, but it's quite interesting. Okay, so these are 3 different kinds of traversals, in addition to BFS, which I was too lazy to implement, that are very, very useful. Okay, and I think that's enough for today. We'll come back next time. Just remember all these terms, and I'm going to ask you to do these kinds of traversals. So maybe think about that before you start the next lecture. So yeah, that's all I have for you, and I will see you in the next one.